When we hear the word explosion, we usually imagine fire, smoke, and destruction. Movies teach us that explosions are loud, bright, and violent bursts of flames. But scientifically, that picture is incomplete. An explosion is not defined by fire. It's not even defined by destruction. An explosion is defined by how fast energy is released. In fact, some explosions don't involve fire at all. Others release less energy than you'd expect, yet cause massive damage. So today we're going to answer a simple question. What is an explosion really? And to understand that, we need to talk about energy, pressure, and time. At its core, an explosion happens when stored energy is released extremely fast, faster than the surrounding environment can absorb or dissipate it. Not heat, not fire, not noise. It's speed. Let's compare two situations. If you burn a piece of wood in a fireplace, it releases energy slowly. Heat escapes gradually. Gases expand calmly. Now imagine releasing that same amount of energy in a fraction of a second. Suddenly, the surrounding air cannot move out of the way fast enough. Pressure builds instantly, and the result is an explosion. So the key difference between burning and exploding is rate, not amount. Energy by itself is harmless. What matters is where that energy goes. In an explosion, energy is released so fast that it creates an extreme pressure imbalance. The surrounding matter, usually air, is forced to move violently to compensate. This is why explosions create shockwaves. Air is pushed outward faster than sound can travel. That sudden displacement is what causes damage. And this is also why explosions underwater are often far more destructive than explosions in air. Water is much harder to compress, so pressure travels farther and faster. Same energy, very different result. To understand explosions, we need to understand pressure. Pressure is simply force applied over an area, caused by particles colliding with their surroundings. In gases, pressure comes from molecules constantly hitting walls, objects, and each other. Increased temperature, and molecules move faster. Increased confinement, and collisions become more frequent. An explosion happens when pressure rises faster than it can escape. This is why confinement matters so much. A fire in open air burns. The same reaction inside a sealed container can explode. This part surprises a lot of people. Some of the most violent explosions are purely physical, not chemical. A classic example is a steam explosion. When water is heated extremely fast, it can instantly turn into steam. Steam occupies about 1,700 times more volume than liquid water. If that expansion happens suddenly and in a confined space, the pressure increase is catastrophic. No combustion required. No flames needed. Just physics. Now let's make an important distinction. Chemical explosions. These involve rapid chemical reactions that release energy. Examples: TNT, gunpowder, gasoline vapor. Energy is released by breaking and forming chemical bonds. Physical explosions. These involve rapid phase changes or pressure release. Examples: steam explosions, pressure vessel failures, rapid gas expansion. No chemical reaction is necessary. In both cases, the damage comes from pressure, not chemistry. This is where things get more technical, but still intuitive. Combustion. Combustion is a reaction that spreads slower than the speed of sound. It relies on heat transfer. Flames move progressively through material. Most fires fall into this category. Detonation. Detonation is fundamentally different. The reaction front moves faster than the speed of sound. Instead of heat driving the reaction, a shockwave does. That shock compresses material so violently that it triggers the reaction instantly. This is why detonations are far more destructive than normal fires. A shockwave is not just a loud sound. It's a sudden, extreme spike in pressure. Normal sound waves gently compress and decompress air. Shockwaves do it violently. The pressure jump happens almost instantly. This is why shockwaves can shatter glass, collapse buildings, damage internal organs, and importantly, Shockwaves don't need fire to exist. They are mechanical phenomena. One of the biggest misconceptions is that bigger explosions always cause more damage. That's not true. Damage depends on energy release rate, confinement, medium, air, water, solid, distance. A relatively small explosion in a confined space can be deadlier than a large explosion in open air. That's why industrial safety focuses so heavily on pressure control. Some metals, like sodium or potassium, explode when they touch water. But again, fire is not the main factor. These metals react violently because they release hydrogen gas. The reaction releases heat extremely fast. Hydrogen ignites almost instantly. Pressure builds faster than it can escape. The explosion is the result of speed, not just chemistry. This connects directly back to our definition. Explosions are not always accidents. We use controlled explosions every day. Examples: internal combustion, engines, airbags, rocket propulsion, mining and demolition. In these systems, engineers carefully control energy release rate, direction, timing, pressure dissipation. An explosion becomes useful when it's predictable. Understanding explosions is not about destruction. It's about safety, engineering, and control. From preventing industrial accidents, to designing safer vehicles, to understanding natural disasters. Explosions are not chaos. They are physics, happening too fast to ignore. An explosion isn't defined by fire. It isn't defined by noise. It's defined by how quickly energy is released, and how violently pressure responds. When energy has nowhere to go, physics takes over. And it always moves fast. Thanks for watching this video about how explosions really work. Keep exploring the science.